Mission Control fired 3 explosive bolts. The small probe disengaged from Galileo. Its goal was to penetrate the atmosphere of Jupiter. With the probe on its way, Galileo fired its engines, setting a new course to bring it into orbit around Jupiter. The images it took were thousands of times more detailed than any taken before. Then, 2 months out, there was a disaster. The tape deck used to record the vital data jammed.
What they discovered was that this tape recorder, if it was run at very high speed, was prone to the tape actually getting hot and sticking.
And so we re-engineered the mission so that we would only use the slow speeds of the tape recorder, and we didn't use the whole thing. So that, coupled with the antenna, really limited the amount of data and how fast we could send the data back to the Earth.
The malfunctioning tape deck was a bitter blow. 5 months had elapsed since Galileo launched its probe. Soon it would plunge into Jupiter's atmosphere to measure its water and other elements. After the impact with the comet Shoemaker-Levy 9, scientists were left with fundamental questions about how Jupiter and the planets formed. Could this tiny probe give them the answer they had been waiting for? The small probe needed to enter Jupiter's atmosphere at precisely the right angle. Too steep and it would burn up. Too shallow and it would be thrown off course.
Everything was calculated to just go in at just the right angle, and it had a big heat shield that was protecting it. Very tense moments as this probe went in.
2 minutes of aerodynamic braking slowed the probe to the speed of sound. A drogue parachute was deployed. Then, silence.
There's a period when a probe goes in where you can't receive radio signals from the probe because of the tremendous heat that's being generated as the probe hits the atmosphere.
As the probe slowly descended through 200 kilometers of atmosphere, it collected the data and relayed it back to Galileo and then to Earth.
And it's trying to measure all the components that are going into Jupiter. What is it made out of? Sulfur. What are the noble gases? The neon, the argon, the krypton. How much is there? How much water is there?
As the probe dived into Jupiter's atmosphere, scientists were convinced they would find the layer of water vapor the comet had revealed, giving vital clues to the planet's creation.
And I even announced a prediction at a scientific meeting, offering to bet anyone in the audience $10 that the probe would find more than a certain amount of water.
But instead of water, the probe drifted through thin, wispy gases. It had flown into a downdraft, a dry gap in the clouds. Where was the water they had expected to find? Jupiter must have both dry areas and wet spots.
What they discovered was that Jupiter has some long-term weather patterns, spots that move around that they didn't really realize were there before.
The probe went deeper still, but there was almost no evidence of water. Less than an hour's worth of data was about to trigger a revolution in our understanding of how the solar system formed. The probe detected a high proportion of heavier elements like argon, krypton, carbon, and nitrogen. It found levels 2 to 3 times higher than found in the Sun. These elements only condense at extremely low temperatures, lower than the temperature found at Jupiter's present position.
We learned that the atmosphere of Jupiter has chemical constituents that came in with very cold material from the outer solar system.
For astronomers, the discovery was a bombshell. The presence of these elements meant Jupiter must have formed in a different way from the Sun.
This little probe, in one felt swoop, showed us that all of our ideas of how planets were formed were wrong. We didn't understand how the planets were made, and we didn't understand the early solar system.
The small probe's discoveries shocked the scientific community. Could the giant planet have formed further out in the solar system where it's colder, then migrated into its current position? Or did comets or asteroids bring the heavy elements and water to it? After 58 minutes, and before the answers became clear, the probe fell silent, burning up in Jupiter's inner atmosphere. The probe had given scientists some remarkable insights into Jupiter, its atmosphere, and how it formed. But questions remained. In 2011, a new mission, Juno, will attempt to find answers, closer to Jupiter, and gather more information than ever before.
What we're really after with Juno is the ingredients. From the ingredients of Jupiter, we're going to figure out the recipe. And that's what's going to tell us how planets are made.
With the probe having completed its work, it was now time for Galileo, 200,000 kilometers above Jupiter, to turn its attention to another long-standing mystery, the planet's weather. How can storms 3 times the size of Earth get so big and last for over 300 years? Jupiter's weather is a maelstrom of swirling clouds, lightning storms, and massive hurricane-like vortices. For the Galileo team, it was a mystery. On Earth, weather like this is powered by the heat of the sun. But Jupiter is 800 million kilometers away, so there must be some other source of power. Its most famous feature is the Great Red Spot, a storm whose clouds tower over 8 kilometers above the atmosphere and plunge deep into a chemical soup below.
The red spot is red because of the chemicals that are trapped there in the center of the red spot have been baked and cooked by ultraviolet light and have turned red.
Astronomers have watched the Great Red Spot for at least 300 years. On Earth, even the biggest storms only last about 2 weeks. So how does the biggest storm in the solar system, 3 times wider than the Earth, get enough energy to rage unchecked for centuries? Scientists believed smaller thunderstorms could hold the answer. In order to solve the mystery, they had planned to video the Great Red Spot and other smaller storms in action. The Galileo team hoped that understanding the mechanics of these turbulent weather systems would reveal the source of their power. With the high-gain antenna out of action, this simple solution wouldn't be possible. The team back at Mission Control needed a new approach.
Instead of making long, continuous movies, we made 3-step movies. You watch the red spot, you come back a few hours later, you watch it again, and so it's just a 3-step movie instead of a continuous movie.
Galileo homed in on a turbulent area of small white spots, which scientists believed were caused by convection or rapidly rising air. If these were storms, they would need to find proof. They needed to locate another of Jupiter's most extraordinary features: lightning bolts 1,000 times more powerful than on Earth. But these are only visible at night.
Jupiter is 11 times bigger than the Earth. It's really big. If you look at this globe, you can see a few intense white-colored spots, small, intense white-colored spots. And when we got around behind Jupiter and looked at the night side, it was those very white-colored spots that had the lightning in them, and no place else. So that identified where the thunderstorms were.
Having identified the thunderstorms, the next step was to find out whether these small white spots can grow into larger ones. Galileo was in the right position at the right time.
There were some white ovals that formed in the 1930s, 3 of them, and they had been around for 60 years when suddenly two of them merged.
Galileo watched as two of the ovals merged to form a larger, more powerful storm. 2 years later, the third oval also merged, forming one large storm in a belt below the Great Red Spot.
And then it had slowly turned red, so that it resembled the Great Red Spot, but not quite as big.
Nicknamed the Red Spot Junior, it was hoped that observations of its birth might also help to solve the mystery of where these large storms get their energy. Jupiter's larger storms swallow smaller storms. This is how something as large as the Great Red Spot came into being.
It's like a food chain where the big fish eat the little fish and the little fish eat smaller fish. And the primary harvesters of energy on Jupiter are the little thunderstorms.
This accounted for the source of all the energy, but it didn't explain why these vast storms last for so long. Conditions on Jupiter are so turbulent that the storms should blow themselves apart. On Earth, vortices such as tornadoes soon die out, but on Jupiter, vortices last for years. It is the fastest spinning planet in the solar system, turning 22 times faster than Earth. Scientist John Arnaud thinks this rapid spin explains the stability of Jupiter's storms.
In rapidly rotating systems, vortices can be long-lived. It's very surprising. Normally we would think they'd shred themselves. They never do. What we've learned from these missions is that it's very coherent, is that it's very stable.
When two different colored dyes are mixed in a rotating jar of water, the results are startling.
At first, what looks like it's going to be a mess quickly turns out not to be a mess. Instead, we generate two large-scale vortices that you'll see are going to be very